Thank you very much. Thank you all for attending. Very good. So I'd like to talk to you a little bit today about the importance of quantum, not only in economic growth, but also in creating resiliency for countries. And note to all, don't use this information for your own investment. So let me start with the overall economic picture. And those figures come from McKinsey & Company, the latest report that they've done, the Quantum Monitor for 2026, that shows that the expected value created at an economic level by 2035 is $1.3 to $2.7 trillion a year. This is yearly incremental GDP created. Last year, they had predicted 1 to 2. So what that tells us is that not only is the impact expected to be very large, but it's also growing in size. If you think about AI, I think the impact is around 4 trillion a year for AI in general. The second really interesting point is that the number of jobs, according to the Quantum Insider, that quantum will create by 2035 is 840,000 jobs. Out of these 840,000, if the universities keep graduating and teaching students at the same pace, we will probably have 250 by then, which means there is about 600,000 jobs that are vacant. There's a gap of 600,000 for those who can get faster to train their students, their population, to take advantage of. The second thing that we've learned from AI is that the early movers capture a large proportion of the value created. And what does it mean to be an early mover? It means to start with the right infrastructure, whether you're acquiring it or manufacturing it. It means using this infrastructure to train people and develop the talent. And this will then lead to economic value capture. And the cycle repeats. So it's really important for nations and for organizations to be on the early side of the cycle in order to capture the value that will be created. But all of this does not come without risks. This is another chart that was created by McKinsey that showed a year and a half ago that if you look at how fast quantum computers are growing in size and how fast the algorithms are improving, these two curves will intersect somewhere near 2035. And this is when encryption, the highest level of encryption that is widely used today, RSA 2048, will be broken. What you see in the orange dots on this slide is our roadmap, the roadmap that IonQ has in terms of how quickly we are going to develop our systems. And according to our roadmap, the two curves will intersect around 2029, much earlier. That change has happened in a year. And I think you might have heard other organizations, Google being an example, citing the same number, 2029. We don't have much time left. So when you look at the overall state of the world and how stable the environment is around us, you realize that security and stability cannot be taken for granted anymore. Not only can they not be taken for granted, I think instability can be taken for granted. We're seeing examples of supply chain shocks based on what we've seen in the Gulf region recently. We've seen encryption, as I showed you on the previous slide, that will be broken faster than we anticipated. GPS communication signal disruption are becoming day-to-day realities. The workforce is being disrupted by AI. And some of the key problems that we face as a humanity are still not being solved fast enough. So if you think of agriculture, agriculture is still being done now using the same fertilizer approach that we had 100 years ago. If you think about how fast we are evolving in terms of solving some of the health problems and our ability to come with newer and better drugs, or creating batteries that are 10 times more performant, all of those at the heart of them, or many of those, rely on our ability to model how molecules, atoms, and electrons interact with each other. Quantum phenomena that are hard to model using existing classical tools, but better positioned to be solved using quantum. So if the industrial age was driven by energy, you need to have the energy to power the machines. If the internet age is driven by information and the AI age is driven by the availability of compute, we believe that the quantum age is going to be driven by what we call sovereign infrastructure. And I'll talk to you a little bit more about this sovereign infrastructure and why IonQ is well positioned to bring it to Korea and to the world. Our goal, as you think about nations as well as the world, is to address this need for growth and resiliency at the same time. You can't look at growth as being the goal without, at the same time, building the foundations for resiliency. Because what we have seen is that these foundations are going to be shaken and are shaken every day on a regular basis. So let me tell you a little bit why IonQ can help there. First, a quick overview on IonQ. We are the largest pure-play quantum company in the world. And by pure play, I mean we only do quantum. Quantum is not a small add-on to our business. It's the core of our business. We are present across all 5 continents. We're working with leading organizations around the world, many of which in Korea here. And we're growing very fast, both organically and through acquisitions. As a result of this, IonQ is today the only company in the world that has all quantum technologies under one roof, from quantum computing to quantum networking and security to quantum sensing and quantum in space with satellites that Capella Space, one of our latest acquisitions, has deployed around the world. Why is that important? It's important because when you start connecting different parts of quantum, you capture synergies. If you have a quantum sensor connected using an entangled communication network to a quantum computer, you can send the information from the sensor to the computer in quantum format. And that enables you to get so much more info from the same sensor, up to 10,000 times more information from your sensor. You can connect quantum computers together using an entangled network to let them act as one. There are many use cases where the ability to have the different building blocks of the quantum stack can only be enabled if you control the end-to-end integration between these building blocks. This came as a result of multiple acquisitions, over $4 billion spent over the past 2 years that added to the core capabilities that IonQ have and continue to develop. The latest of which is still going through the process of being approved is Skywater, a fab location in the United States. The result of this is an acceleration on all these levels. So if we look at the quantum computing side, our roadmap is probably 5 years ahead of anybody else in the industry. And this came as a result of integrating the capabilities of Oxford Ionics in the UK and their ability to do electronic qubit controls to the existing platform that IonQ has for our quantum computers. The result is removing one of the major bottlenecks that we had in our production, which was the use of large, bulky, finicky lasers that prevented us from growing as fast as we wanted and maintaining the quality and the fidelity that we want. With this roadblock removed, we have now a roadmap that increases very fast, not only in size and number of qubits, but also in the fidelity of these qubits. And this is critical. And this is represented on this graph by the ratio of physical qubits to logical qubits, which is about 1 to 12 to 1 to 25, much, much better than the 1,000 to 1 that you see in some of the other modalities. So what does it mean? If you have a better ratio of physical to logical, it means that you can create more logical qubits that will then become essential when you have a fault-tolerant machine. In this example, if you have 10,000 physical qubits, at a ratio of 25, you can get 800 logical, whereas in other modalities, you would have 40 logical, so 20x improvement. But all of this, logical qubits, physical qubits, why do you care? At the end of the day, the only thing that matters when using a quantum computer is, can you get a result that is high fidelity, a result that really matters, and how fast does it take to get these results? And what we have shown is that on our roadmap and our focus is to get the fastest time to a usable solution using our computers. Other modalities might be much faster in the way they process 2-qubit gates. It doesn't matter. The question to ask is, how long will it take me to get to a usable answer? Many modalities will not get you to a usable answer in the current state of their computing platforms. And those who get you, the few who get you to a usable answer, can take a very long time, even though they might have faster 2-qubit gates. The example that you see here is that when you have a high-fidelity, low-noise computer, it's like when you're shooting at a target, the first thing they tell you is get all of your bullets close to each other. Doesn't matter if they are on target or to the side, but get them close to each other. And the second part is then move them to the center of the target. IonQ, because of the fidelity of our technology, gets all the bullets very close to each other. And that means that when you are running multiple iterations to find an answer, you need to run fewer iterations than many of the competing approaches that are very scattered by the nature of their low fidelity. This is an example that shows that with 5,000 shots, you're getting an answer faster in portfolio optimization than 1 million+ shots using a leading competing platform. So time to usable solution. Forget qubits, speeds, feeds, whatever metrics. Can I get a usable solution, and how fast can I get it? The examples that you see here are ones that today are enabled by the current state of our technology, from portfolio optimization to computer-aided engineering and computational fluid dynamics in the case of Synopsys and ANSYS, which is really important in Korea given the manufacturing industry, to logistics and route optimization with Einride in Europe, to reduction in error classification with LLMs and AI with quantum Basel, and finally, pharmaceutical acceleration of time to solution compared to other previous approaches to quantum modeling with AstraZeneca. Those are just the starting examples. As the machines improve in size and quality and fidelity, and as the algorithms improve in terms of algorithmic innovation, we will see many of those increase. We are already, as an industry, above what you can simulate using classical compute. We are in the area of unknown, and we're moving very fast in this area. I just want to tell you how fast we are moving. If you look at our roadmap, going from 36, sorry, it's not on this slide, so just from 36 to 100 qubit. Every time you add a qubit, you double your computational space. From 36 to 100 over the past 2 years, we've doubled the computational space on average every 10 days. In the next 2 years, from 100 to 1,000, we will be doubling on average every 2 hours. And in the 2 years after that, from 10,000 to 2 million every minute. Keep this in mind. Computational space doubles, or exploration space doubles every minute. And compare this, it's not exactly the same metric, but compare it to doubling our compute capacity with Moore's law every 2 years. Doubling every 2 years with Moore's law versus doubling the exploration space every minute with quantum. Anybody with doubling every 2 years, we've created the internet, mobile phones, LLMs, cloud computing. Imagine doubling every minute. Anybody who tells you that they have a good sense of what can be created is lying to themselves. Nobody has an idea. Anyways, moving from compute into networking and security. How do you secure your environment if you have less than 3 years before the existing encryption is going to be broken? You secure it by adapting a number of proven technologies, including post-quantum cryptography. What is post-quantum cryptography? It's using harder to break mathematical algorithms compared to the ones that we have now. Sorry. The other option is quantum key distribution. Quantum key distribution is not mathematically based. It's physically based. It's essentially having an entangled communications between two parties. And if anybody can get in the middle, the entanglement will be broken. The communications will be, the channel of communication, you will know that it's been intercepted. And you will start a new session, and you will know that you're safe. IonQ does both. We use all the tools available for encryption, including post-quantum cryptography, quantum key distribution, applying each one in the area where it applies best, so that we can get both governments and enterprises, banks, healthcare institutions, to a secure state much faster than any other alternative that would have taken years to secure one's network and data center. On the satellite side, I mentioned satellite earlier. Satellites play a key role in quantum going forward. I mentioned having sensors on board of satellites. Those sensors could be also time modules, i.e. atomic clocks that are one of the varieties of quantum sensors with a precision such that even if your GPS network is done, using the synchronization based on these clocks, you can create replacement alternatives for navigation. You can also have communications on these satellites. So if you're securing your network and you need to hop over an ocean or a desert, you can use your satellite to be able to expand your network security way beyond what you can do on land. Satellites can also one day have quantum computers on board. We're not there yet. It's going to take some time. However, the current utilization of quantum satellites in defense, in communication, and in sensing is proven. It's a technology that has existed for some time and accelerating. I'd be remiss to mention that when we talk about sovereignty, when we talk about securing and increasing resiliency, it's not just for companies, it's also for governmental institutions. Today, governments are looking at quantum computers to enable everything from education to finance, transportation and logistics, public safety, etc. And IonQ has adopted a hub approach, a sovereign quantum hub approach in many of the countries where we are present. And what does it mean? It doesn't mean to just sell our infrastructure. It means to create around this infrastructure the ability to innovate, train the next generation of students, bring new startups, secure communications and governments, and activate this investment. For Korea specifically, you probably know that not only do we have, in partnership with KISTI, a quantum computer that will be installed on the premises of KISTI to enable education, research, and other use cases. We also have probably the largest Western quantum-safe network in Asia, connecting Seoul to 48 different locations and administrations around it using quantum-safe communications. We also are today in discussions with a number of innovators in Korea to talk about manufacturing. How do you extend manufacturing to Korea? How do you extend application development and solution creation using quantum in Korea? So we're seeing the investment that the Korean government, education institutions, and private sector in Korea as a fertile ground for IonQ to come and build this sovereign quantum hub and accelerate and multiply your investment with our investment, co-investment, and partnership. I want to thank you for taking the time to listen to me, and I'm happy to answer any questions. Yes.
Oh, thank you for mind-blowing presentation. It was amazing. And then I'm not sure I will not buy stock or not, joke. So when you show the number of qubit that the roadmap, yeah. I saw there is sudden increase between 2026 and 2027. I wonder what happened there.
Yeah, the sudden increase, I think, is a jump from 256 to 10,000, if my memory is...
Well, yeah. right, that one, yeah.
Yeah. This is the result of the electronic qubit control technology that I mentioned. Before that, every time you had to increase your number of qubits, you had to add something called Raman lasers. Those are lasers used to run the operations, to run 2 qubit gates and 1 qubit gates. They are much harder to scale. They are very sensitive and finicky. And so by adopting a different technology which enables you to control all these operations, not by using a laser, but by using antennas embedded in your trap and electronically controlling these operations, you've created the ability, you've removed a bottleneck. And this explains the jump and the continuous accelerated growth.
Thank you.
Yes.
Thank you for the presentation, and upon the previous question, I have also another question in that chart. That every hardware platform shows they can make the qubit larger and larger. But in this chart, I found out that there are a same ratio between physical qubits and logical qubits. And is there any evidence, or could you guarantee that even physical qubit is over 1 million, still there is a still ratio between physical qubit and logic qubit? It is stable. So how could you? Is there any evidence on that?
So your question is there any evidence that when you add that many qubits, you can keep a small ratio of physical to logical? And the short answer is, the reason why this reasoning is done is because the assumptions around how you're going to scale show that the scaling approach enables this ratio. How exactly it's going to work, you probably would have a discussion with one of our engineers who can take you through the details. But I'll add one thing. This ratio comes from the fact that we have last year demonstrated the highest physical fidelity of 99.99% ever done in the industry. So will this fidelity remain stable, or can we increase the fidelity at the physical level as well? In which case, even if you lose some of the ratio, you will catch it on a higher fidelity on the other side. I wouldn't know how all the factors work together. I know that we have much smarter people than me in the organization who might be able to answer your question.
Thank you very much for a nice talk. And I remember that you, among your slides, with the slide title "Opportunities Comes with the Risk" Q Day in 2019. That graph. Yeah. So in your graph, you're showing, in some sense, pretty much conservative view. In sense, from the viewpoint of the one who take cares about the cryptography. Anyway, you're saying that the RSA 2048 will be vulnerable from the year to 2028. Yeah. So are you? So are you saying that such a cryptocurrency based on that RSA system is also vulnerable? And are you is IonQ thinking about anything about it? Yeah.
So those are two separate questions. The answer to the first one is yes. If you think, for example, about the Bitcoin network, it's secured using ECC security, which is easier to crack than RSA 2048. So you would think it might be cracked earlier. I'm sure that the miners running these networks realize that they need better encryption if they want to save the billions and hundreds of billions of dollars, sometimes trillions of market size they have. There are people who are thinking about it and are saying, look, we will probably know if somebody broke this encryption first by looking at the dormant accounts. looking at accounts that haven't been, maybe people lost the keys or somebody hasn't touched it and isn't in control anymore. And those would be the earlier targets, would be the canaries in the coal mine. How fast will the industry adopt new encryption is a question mark. And in my opinion, it's not a technical question mark. It's a organizational question mark. How can you convince a large network of people with decentralized decision-making to all move in one direction? Of course, this is beyond what IonQ is doing and is not an area that we're engaged in, but those are questions that the industry is asking itself.
Thank you.
Yep.
Yes, due to time constraint, there will be the last question from the floor, please.
I'm working in investment side. As you mentioned, in the importance of the co-investment between the IonQ and Korea, is there any potential and huge challenge or bottleneck against the co-investment?
Is there a challenge against co-investment? I don't know if I'm answering your question correctly, but every company can decide to co-invest for any reasons. You know, sometimes it's strategic reasons. You're building together a new technology and you're co-investing. Sometimes it's a commercial reasons to enable penetration of a market faster. I don't think there are any legal restrictions from co-investment. It's a strategy of the company. But am I answering your question correctly?
Yeah, enough.